Okay, so we are on lesson 19, and our discussion, the next four lessons, this lesson up until lesson 21 or 20, let me check, up until lesson 22 are actually just going to be about the Doppler effect. And then our learning outcomes for all of those lessons are that at least you should be able to state what the Doppler effect is, and as this definition is given in your examination guidelines that I really encourage you guys to have and to go through and to know very well. They say that it is defined as the change in frequency or pitch of the sound as detected by a listener, because perhaps the sound source as well as the listener have different velocities relative to the medium of sound propagation. So also you should be able to explain using appropriate illustrations the change in pitch observed when a source moves towards or it moves away from a listener. And you should also be able to solve problems using this equation. I'm thinking that you guys are already familiar, or at least you have seen this equation when you were dealing with the Doppler effect during the course of the year, when either the source or the listener is moving. And also another thing that is important, you should be able to state the applications of the Doppler effect. So these are some of the things you might be tested upon. And then with red light as well as red shifts, you should also be able to explain first what are red shifts, and then use the Doppler effect to explain why we conclude that the universe is in actual fact expanding. All of these things are going to be discussed upon in the next lessons. So for today's lesson, it's just going to be an introduction to the Doppler effect. So let us just get straight into it. Okay, so I would like to first apologize about the flashlight. The phone that I normally use to take these videos dropped in a pot of boiling water. Don't ask me what I was doing, but yeah, so the quality on this one is not so good, but I'm hoping that we can actually get through this next four lessons, and hopefully I'll be able to fix that phone. So okay, let us start our discussion in terms of the Doppler effect with defining sound. So what is sound? Sound, we can say it's caused by vibration. So when something is vibrating, it's gonna cause a sound. So in actual fact, this means that sound is a sort of a wave. So we can draw a wave. This is how you normally draw waves. And just to do a small experiment, so for example, if you put your finger on your throat and make a sound, you'd actually feel the vibrations, like you'd actually feel your finger, your voice box or your throat making those vibrations. So yeah, we can, like I mentioned, we can draw a wave to represent sound. And let us say here, the top here, we call those crests. So that is the crest of your thingy, so crest. And we can now define something we call a wavelength, where what we call a wavelength, and we represent a wavelength by that symbol lambda. We call that, it's a Greek letter lambda. And we say that that wavelength is the distance between two consecutive crests or troughs. So the top part, we call them crests, and these ones we call them troughs, as you probably know by now. And the wavelengths are normally measured in meters. So this is a wavelength, and we measure it in meters. Okay, so so another property of sound that we can define is frequency. So frequency is given by the letter F, and we measure it in hertz. Okay, so that is another property that we can define, and this frequency is defined as the number of times that the wave is produced within a certain period. So let us compare two waves. Let me draw another wave just below this one. Let us start, and then we say perhaps this is the wave that we're looking at. So these two waves are produced within a certain period of time, and if you can find the wavelength of this so from crest to crest, right? And then what do you notice about these two waves? Let's call this wave 1 and let's call this wave 2. You can just say lambda 1, lambda, okay, let me not say lambda, that's gonna get a bit confusing. So for wave 1, what are we noticing? So wave 1 actually has a lower frequency, or let us start here. Wave 1 has a longer wavelength, but it has a lower frequency f. Wave 2, on the other hand, has a shorter wavelength, but it actually has a higher frequency. Why? Because then this wave here is produced. So if we take this as a single wave, this wave is actually produced a number of times in comparison to this. So you see, in that period that we've defined, maybe from here to here we define a time period, there are more waves produced for this wave than for this one. So we would conclude that wave 2 has a higher frequency, but a higher frequency always corresponds to a shorter wavelength. That is something important to know. A longer wavelength corresponds to a lower frequency. And then while we're talking about this thing, we can also define another thing that we call pitch, or a measure of how a pitch can be defined as a measure of how high or how low something sounds. So if something sounds a bit loud, we say it has a higher pitch. If it sounds lower, we say it has a lower pitch, and a lower pitch corresponds to a lower frequency. So this wave would have a lower pitch, so the sound of it would be lower, right? And then this wave will have a higher pitch, so its frequency is high as well as its pitch. So if this were two sound waves, if they were played to you, this one would make a louder noise, or a louder sound, in fact. So now what are we noticing about all of these things is that if for higher frequency the two crests, or the two consecutive waves, the two crests of the thingy, they are closer together. But here for a lower frequency, these two crests are a bit of a distance apart. So now, while with this information in mind, let us now talk about a sound relative to movement. So keeping everything that we have learned so far, let us now consider sound relative to movement. I think my handwriting is getting better as I'm making these videos. So now let us consider a situation where you are, we call you an observer or a listener. So you listening, and then we have a car. There's a car with a huge speaker playing music. So the sound coming out of that speaker, I feel like I need to leave a little bit of space there. So there's a car, and there's a speaker. There's music coming out of that. So we represent those waves, using these circles. And I'm trying to make sure that the spaces between the waves' lengths, the crests of these waves, is the same. So for example, if we were to draw this, so this point over here maybe will be this point, and then this will be this point, and then this will be the third point. And then remember, sound is just propagating in all directions. Okay, so in this situation, this car will emit a frequency. We call it the source, the frequency of the source. Let's say it was 100 hertz, and then it's stationary, it's not moving, so its speed is 0 meters per second. And then you as the listener, your frequency, the frequency that you will hear, will be the same frequency as this one. So you also hear the same frequency, considering that both of you are actually stationary. So this is the velocity of the observer, which is 0 meters per second. So if both of you are stationary, whatever frequency that is produced by your your source. It will be the same frequency that you hear. But now something interesting happens when for example, now we have moving, either you or let's say you or the source is moving. So when you and the source are moving, so now this is you quickly, and then you have a car, the same car, playing a music. Let us consider another person here, another listener or another observer. So let's say in this case you are stationary, so we say VL is still 0 meters per second. Even this observer on this side is still stationary. And then this car with its speaker, it's moving to, what you got it, it's moving towards this observer. It's moving towards this observer, but in actual fact it's moving away from this one. Okay, so now what will happen is that those waves that we had initially drawn, so here we are, so remember this is your speaker, they will now start looking like this. On this side where you moving, it's moving towards the thingy, there will be less spaces, so you draw them like this. So on this side, this wave, the crests or these waves would be apart from each other, meaning we'll have a longer wavelength on this side. So remember, a longer wavelength corresponds to a lower frequency, meaning that the frequency that this person, this observer, which we call FL, will actually, let's say the frequency of the source was still 100 hertz, will actually be much lesser than the frequency. So this person would perceive the frequency to be lesser. It doesn't mean that the car is producing a lesser frequency, no, but this person hears the frequency to be lesser. So meaning that the frequency of this person would actually be less than 100 hertz. But on this side, you see now on this side, because it's moving towards this person, those two full waves are now kind of closer packed together in that period of time. And what would happen, so if they are packed together, they have a shorter wavelength, and a shorter wavelength corresponds to a higher frequency. So this person would actually perceive a frequency that is higher than the frequency of the source. Let me just use small letters there. That is higher. It doesn't mean that the car is producing a higher frequency, it's still producing the same frequency, but this person is hearing a much higher frequency, meaning the frequency of this observer will actually be greater than 100 hertz. So those are the types of scenarios that we normally talk about in the Doppler effect. It can also be, this situation can also be different, where the source is stationary, and what happens is that this person is moving closer. Their perceived frequency will still be larger because the spacing between those sound waves will be packed together. Or in this case, this person will be moving away while your car or whatever your source is stationary, and then your frequency will still be lower than this. I hope that is making sense. So the important thing that I wanted to kind of emphasize is that perceived, it's something that you perceive. It still produces a frequency of 100, but this person is hearing it, hearing a higher frequency because they are approaching each other. This one is hearing a lower frequency because this car or them are moving away from each other. So in this case the wavelengths are longer, or in this case the wavelengths are shorter. So that is something very important that we have to know. So what can we conclude is that an apparent change in wavelength, it causes a change in the perceived frequency. So now that we have defined all of that, we can actually now describe what do we mean when we talk about the Doppler effect. So when we talk about the Doppler effect, we are actually referring to the change in frequency of sound perceived by a listener because the sound and the source the sound source and the listener have different speeds. So remember, it's either they are moving, it's either the source is stationary and the person is approaching, or the person is stationary and the car is approaching, or the source is stationary and the person is moving away, or the person is stationary and the car is moving away. So that perceived frequency that the person is, that's when we start defining the Doppler effect. Let me say it again: the change in the frequency of sound perceived by a listener, because the sound source and the listener or observer have different speeds relative to the medium in which sound is propagated. So please know those definitions while we edit. So normally this is the formula that you were introduced to in class, and when we have, in terms of the Doppler effect, it says that FL equals to V plus or minus VL, all of it divided by V plus or minus VS multiplied by FS. So let us try to define what each of this means. So this is the frequency of the listener, this is the speed of sound, this is the speed of the listener, this is the another, so these two are the same. This is the speed of sound, we already defined it. This is the speed of the source, and this is the frequency of the source. So it's very important to know. So remember, speed is measured in meters per second always, and your frequency would then be measured in hertz. So do not confuse this speed. This is just the speed of sound. So there are three speeds that are of interest: the speed of sound, the speed of the listener, and the speed of the source. Okay, so now let us, when you're writing, another important thing when you're starting to answer these types of question, and perhaps you ask to find the frequency of the source, always start with this equation, and it's given at the back of your question paper on your formula sheet, right? And then another equation that is important is V equals to F. So the velocity or the speed of sound is actually equals to the product of the frequency and the wavelength. So V is the speed of sound, F is the frequency of sound, and then this is the wavelength. So sometimes you're not given what V is, and you have to calculate it using this formula. Okay, so I think that actually brings us to the end of part of the first lesson. In the next lesson, we're going to discuss 4 different situations that you would normally be examined on in your exams, relative to using this formula. Okay, so thank you so much for watching. We will meet again on the next lesson.